Good evening, everybody, and thank you for joining us for our first in person talk post COVID. My name is Pradeep Kumar, and I'm the chair of the Oregon chapter of the IEEE Communication Society. And without further ado, I'd like to introduce you to our esteemed speaker today. Kumar Vijay Mishra is a senior fellow at the U.S. Army Research Laboratory. He holds a PhD in electrical engineering and an MS in mathematics from the University of Iowa, as well as MS in electrical engineering from Colorado State University. Mr. Mishra also serves as a research scientist at the University of Maryland, where he advises radar startups and holds an honorary research fellowship at the University of Luxembourg. He has held research positions at several prestigious institutions and is recognized as an IEEE Distinguished Lecturer. Dr. Misra is actively involved in IEEE committees and editorial roles in IEEE journals, focusing his research in radar systems, signal processing, remote sensing, and electromagnetics. Please welcome Dr. Misra.
Good evening, and thank you for the nice introduction, and thank you for organizing this distinguished lecture of IEEE Communication Society. So today I'm going to talk about this very exciting topic, which has gained salience in past few years, that is integrated sensing and communications. It also goes by joint radar communications or dual function radar communications, and we'll get into the terminology in a moment. It's very difficult to summarize all the new frontiers in this topic in this roughly 50 to 55-minute lecture. Usually, I do a 5-hour tutorial on this in various conferences. So my objective today is to first give you a historical context of this problem of integrated sensing and communications and where we are in the state of the art today. And then I'm going to pick some interesting examples. And as we progress through the presentation, I also go from a very, very theoretical example to a more practical example. Because by the end of it, I don't think anyone wants to see any theorems or anything. So theory first, and then we go to more applications. So I'm not going to read all of this. Pradeep already explained it. I just want to point out, apart from my role at Army Research Lab and University of Maryland, I'm also a technical advisor to these two very promising startups. First is Hertzwell, which is based in Singapore. It is Asia's first automotive radar startup. And second is Aura Intelligent Systems, which is based in Boston. It works on 5G imaging radars, that is using 5G waveforms for imaging and sensing, which is very much related to the topic we are going to discuss today. And I'm mostly interested in radar, but I explore its connections with signal processing, communications, electromagnetics, and remote sensing. I would like to acknowledge a number of my colleagues whose collaborative research will feature in today's presentation from Army Research Lab, Brian Sadler, and various colleagues from University of Luxembourg, where I also have a complementary position. And then Industrial University of Santander in Colombia, Henry Arguello and his students, Edwin, Roman, and Jonathan. I would like to acknowledge funding from ARL and the National Academies, which is based in Washington, D.C., for funding most of this research. In my presentation, I like to include snippets from my favorite science fiction TV shows and movies where the characters are discussing radar. So you'll see throughout this presentation, just to keep things interesting. But the one that you see here is very much related to the presentation or the topic that I'm talking about today. So this scene is from this very popular Apple TV Plus show For All Mankind, which is about a bunch of NASA scientists, and it is set in an fictional storyline in 1960s. And in this scene, these characters are discussing about the interference from solar flare because of heightened sunspot activities on ground-based communications network. Apparently, when the frequency of solar flares is very high, it can jam communications on Earth. Indeed, if you go to the early 1960s and look into the literature in IEEE, there used to be an IEEE journal, IEEE Transactions on RF Interference. And most of the papers that were published in early 1960s were exactly on this topic, interference from solar flare on communications network. So it was such a widely studied topic. So here is a sample paper from the 1963 issue on RF interference from this heightened sunspot activity. So this is an example of natural interference on various emitters on Earth. Today, we are going to discuss man-made interference, interference from emitters such as radar, navigation, positioning systems, on communications, or vice versa, and how that problem is then giving rise to new types of system design. So as you can see, RF interference studies they have been around since 1960s. In fact, the very first paper on joint radar communications could be traced back to early 1960s. Very rudimentary paper on that topic. In late 1970s, NASA did some scattered research on designing systems which have multiple functions, which can double up as both radar and communications. But it was really in mid 1980s that we saw more research on this topic. At the time, US military was deploying this specific type of radar which operates in UHF VHF band. We call it FOPEN radar or foliage penetration radar. To detect intruders in a dense forest or within some very dense vegetation. Now, that radar encountered a lot of interference from TV and broadcast stations, which were installed all over the US from 1960s onward. So mid 1980s, this interference became a serious problem for US military at that band, UHF, VHF band. If we look into FOPEN literature, there are several books that were written just on this topic and several papers appeared in 1980s. The solution that radar engineers found was because the transmit signal bandwidth for that particular radar was extremely wide, they simply put notch filters at the interfering frequencies at the receiver. It didn't cause much signal distortion or degradation in performance of radar because of this very wide bandwidth. So even if you remove some of the frequencies, it still functions very well. So there has been a lot of work since 1960s on this, but it is really in the past 12 to 15 years that we have seen more focus on this particular topic, on interference, spectral interference, and spectrum sharing. The question is why that is the case, why it is happening right now, even though people have been studying this for last time. So there are two primary motivations for this. The first one comes from the wireless communications industry. As you can see from this graphic that I have taken from some industry sources, the number of devices that are connected right now, that number has already crossed 100 billion. It is supposed to dramatically rise in the near future. More devices connected means more data being exchanged between different devices. We need protocols that can support very high data rates in order to connect these many devices. Further, for the future network, 6G or beyond 5G communications, there are demands for very high quality of service to support various futuristic applications related to gaming, infotainment, and so on. And all of those applications, they also require very high data rates, which the current sub 6 gigahertz wireless communications networks, which are our traditional communications networks, they are unable to support those kind of data rates. So the question is, how can we meet demand for these high data rates? For this, we turn to Shannon's famous capacity formula as a guide, which tells us that the capacity C, which dictates the data rate, is governed by three factors. First is lowercase n, which is the number of non-interfering or orthogonal resources. For example, number of time slots could be n, number of subcarriers, so which we know is the concept of OFDM. It could be number of transmit and receive antennas. You increase the number of transmit and receive antennas, which is what we do in MIMO communications, and that has a bearing on capacity. So you can play with n to increase C. Then we have signal to interference plus noise ratio, or SINR. And there's been a lot of work in wireless communications on improving SINR at the receiver, finding different types of transmission schemes so that SINR could be improved and so on. But you'll have to increase SINR a lot to see any appreciable increase in C because they have a logarithmic relationship with each other. So we come to the third factor, which is bandwidth W. Wider the bandwidth, it is better. It is a linear dependence. But we cannot arbitrarily allocate this bandwidth to just one application because first reason is that a lot of spectrum, at least under 6 gigahertz that has already been allocated by national and international regulatory agencies like FCC or ITU to various existing applications. Sub 6 gigahertz spectrum is extremely crowded. Then we can move up to millimeter wave or the so-called low terahertz region, where depending on which country you are in, you can have anywhere from 4 to 7 in the lower millimeter wave, and then upper millimeter wave 7 to 15 gigahertz of contiguous bandwidth. But then there are a lot of players in the market who would like to have an exclusive access to that bandwidth. Because this is a very scarce natural resource, it's difficult to just allocate such a wide bandwidth to just one particular company or one service provider. As you can see from this graphic that I've taken from Ericsson's white paper published in 2022, currently we are most of the wireless communication services, they are in sub 6 gigahertz, that is that blue band. But then for 6G, we are looking into the mid band, that is 6 to 12 gigahertz, or possibly millimeter wave or sub-terahertz band. That's where the focus is, mainly to gain more bandwidth. But then again, even if this bandwidth is available or is unlicensed, it is difficult for just one service provider to use it exclusively. This contest between or the conflict for more spectrum is also not new. I've taken some headlines right from 1980s until very recently. Various companies have been asking FCC for more spectrum, and the problem is only becoming worse now because there are more players in the market, and there is demand for all these futuristic services. Wireless communication industry is booming because of new applications. So this is becoming a problem, how to share this very limited resource with various emitters. The second motivation for joint radar communications comes from the radar industry, in particular, automotive radar industry. As you can see from this graphic, modern autonomous vehicles, they are equipped with several sensors. They have GPS, LiDAR, cameras, ultrasonic sensors, radar, and so on. And the goal of these sensors is not only to guide the driver in a crowded or challenging traffic environment, but also to monitor the general health of the car. We have sensors for tire pressure and various other functionalities of the vehicle, and sometimes also to monitor the physiological behavior of driver and other passengers. So we have in-cabin sensors, could be acoustic, optical, or even radar-based, to measure the heart rate or respiratory rate of the occupants of the vehicle. So there are several sensors in each one of these vehicles. But if we focus on just autonomy-enabling sensors, then chiefly three are very common. First is the high-resolution camera. Provides a very good visual, has a lot of semantic information in its files. But when the visibility conditions are poor, could be in the night or in the presence of precipitation, rain, snow, then its performance is poorer. Moreover, it does not measure Doppler velocity directly. Rather, it infers it indirectly by looking at the change in the movement in its various targets like pedestrian or vehicles across different frames. So it's an indirect measurement of velocity. So we come to the remote sensing sensors, that is radar or LiDAR, which actually transmit a signal and then measure the distortion in the signal that comes back from the target for various measurements. So LiDAR operates in optical range of the spectrum. In optical range, bandwidth is extremely wide. For people who may be familiar with LiDAR or radar signal processing, they may recall that wider the transmit signal bandwidth, higher is the resolution of the sensor. By resolution, we mean the ability of the sensor to discriminate two very closely spaced targets. So at optical range, you have extremely wide bandwidth available, so LiDAR provides the best resolution. But the problem with LiDAR is, first is the cost. If you go in the market and try to buy LiDARs, usually the standalone LiDARs, their cost starts from 12 grand onward. Although there are efforts to bring that cost down, but all of that is still in the research domain. So first is the cost, and a few years ago, General Motors released this white paper where they stipulated that the cost of remote sensing sensors in batch production should not exceed $100. So LiDAR does not meet that benchmark. It's extremely expensive. It also has mechanical scanning. It is mounted above the main body of the car for aesthetic reasons. Some vendors don't prefer that. And mechanical scanning, that is also an issue because you have to mechanically scan the whole environment. It is not electronically. It doesn't illuminate the entire environment at once, which is also an issue. Although I must say that there are works in the research domain on making a electronically scanning LiDAR. Very preliminary research has actually started in this area. So we come to radar, which is an all-weather sensor, at least for automotive applications, because those are short-range applications. Day or night doesn't matter, radar still works. And it works on Doppler principle, so measures the Doppler velocity directly. It's low cost, it can meet that $100 or so benchmark. But then its resolution is poorer than LiDAR because it operates in the microwave range where bandwidth is much smaller than the optical range. And as I mentioned earlier, narrower the bandwidth, poorer will be the range resolution. There are efforts on moving from millimeter wave part of the spectrum, because that's where current automotive radars they operate, to go to low terahertz, where some research studies have shown that you can get near optical resolution with those terahertz radars. But that is still in the research domain right now. At millimeter wave, we don't have enough resolution. So the only way is that you increase the bandwidth in the millimeter wave band. But again, you can't do that just for this one application because there are so many other applications that people would like to have access to that wide bandwidth. On top of this, we have concept of connected and automated vehicles. Vehicles are supposed to be talking with each other, with satellite, with infrastructure, and so on. Because of this, they generate a lot of data that the current short range sub 6 gigahertz protocols like DSRC or CV2X, they are unable to sustain. And as we saw in the wireless communications segment of the motivation for JRC, uh, if there is huge data, then you need wide bandwidth to support that data. So we have this problem that if we want to sense accurately, have high resolution, then you need wide bandwidth. You want these vehicles to stay connected and enable all kinds of futuristic applications, then also you need bandwidth, but we don't have this bandwidth just for one application. So let's look into the spectrum allocation. How is it right now? And there, if we examine various IEEE radar bands, then as you can see from this table, pretty much every IEEE radar band today has some coexisting communication service. And this problem is only becoming worse. So starting from UHF, VHF, from the FOPEN example, now when we go to automotive radars, there is some communication service. And with the advent of new civilian radar applications and new communications protocols, we are expecting that the spectrum congestion is going to increase in near future. Now, this problem does not only have technical ramifications, it also has a lot of legal implications. So I put some headlines here from 2021 to 2022 about two very famous legal cases. In 21, AT&T sued FCC after FCC allocated slivers of sub-6 gigahertz band to unlicensed users. That means that anyone could transmit in those unlicensed, very, very small subband in sub-6 gigahertz. And AT&T argued that this is going to cause interference in their wireless communication services. This allocation should be rescinded. Second legal case was in 22 when FAA asked Verizon to stop transmitting its 5G frequencies around US airports because it was interfering with this one device that airlines use for landing and takeoff for decades, that is the C-band altimeter. Which this example also shows that this problem is not just limited to radar. It goes to other applications and other devices too. So C-band altimeter was encountering a lot of interference. So recognizing the technical and legal implications of this problem, about 12 years ago, DARPA launched the S-SPARC program, that is to design spectrum sharing technologies between S-band military radar and S-band military communications. Later on, National Science Foundation, through various programs, they have expanded the spectrum sharing technology, the research on this technology to various other parts of the spectrum, not just limited to S-band. Now they are looking across all the bands, and every few months I see a new call for proposals from NSF, and some of them I've listed here: SWIFT, PAR, Spectrum X, NERDS, and so on. There are, as I said, implications beyond radar. So radio astronomers have been complaining about interference from communication satellites that is interfering with clean sky observations. Meteorologists have been complaining about interference from Wi-Fi. Sometimes that interference has been misconstrued as a storm or a tornado, and it has led to false reports. So this problem has become very pervasive, and a lot of different communities, technical communities, legal communities, government agencies, they are very actively involved in addressing this issue. So if we look into past 12 years since the launch of SSPARC program, what kind of spectrum sharing technologies have been attempted at so far? And if I want to classify them very broadly, then here is one possible classification. This image is from one of our very highly cited signal processing magazine paper. Uh, if we want to address spectrum sharing, one way could be that radar and communications, they share the same hardware. They can transmit the same waveform so that there's no interference from each other, and then develop better receive signal processing algorithms to separate the radar return from communications messages. So depending on the sharing of hardware, we can have these four topologies. When none of the hardware is shared, either the transmitter or receiver, you get figure A, where radar and communications are transmitting independently and accessing the spectrum independently. Obviously, there will be interference at the receiver from one to the other because they are not coordinated at all. In this case, we focus mostly on researching receive signal processing algorithms to mitigate the mutual interference. This approach is very good for legacy systems where it will cost a lot to change the whole hardware or start thinking of transmission of new waveforms. So spectral coexistence approach, they were very popular during the early days of SPARC. It's not that they are not popular now. In fact, I'll give an example from Army, a very interesting example of some very difficult spectral coexistence problems. Everything else where some part of the hardware is shared, that is spectral co-design. A very general case is figure D, where I am giving an example of a vehicular scenario. So here you have a common transmitter on the red car. It is transmitting a radar waveform, which has been modulated by communications messages. That waveform then interacts with other cars in the environment. For example, the blue car or the yellow car, which for the purposes of this segment of the talk, I'll call them radar targets. And then when that waveform is reflected, it is intercepted by a common receiver on the gray car. And the goal of the signal processing at this common receiver is A, to extract the target parameters, that is the location, Doppler velocity of the yellow and the blue car, and so on. And B, to decode the message that was sent by the red car, because it's a common radar and communications receiver. And you would notice here that the transmitter and receiver, they are not on the same card, they're not on the same platform. So it's a bistatic joint radar communications co-design. They're on different platforms, and this could be extended to the multi-static case as well. This is a very broad classification, but over the past few years, a lot of other types of ISAC technologies have come out, which is not surprising because we have so many different applications of radars. We have so many different types of communication protocols. And when you try to share the spectrum between one of those radar systems with one of these communication systems, usually it leads to a bespoke and a unique solution. That's why there is a lot of literature on joint radar communications where people are trying to share spectrum with one specific type of radar with one specific type of communications. So we already saw a classification based on hardware. You can do this based on waveform. It could be separate waveforms, could be the common waveform from the same common transmitter, or could be the same waveform, but it is shared on time slot basis between radar and communications. Depending on the location of transmitter or receiver, we saw an example of bistatic case. You can make it multi-static. They could be networked. They could also be heterogeneous. One radar could be phased array radar, another one could be mechanically scanning. It's not necessary that when you're trying to share spectrum between different nodes, all the nodes have to be identical systems. So it could be very complicated. Then we have based on performance or functionality, and you would often encounter these terms in ISAC literature. It could be radar centric or comp centric. Although we are interested in optimizing the performance of both radar and communication systems, usually in some applications, that could be the case that you're willing to tolerate degradation in the performance of one of the systems, and you are primarily interested in optimizing the performance of the other. So if radar is your primary system and communications, you're okay with some degradation performance, those solutions are called radar centric. Vice versa, you'll have comp centric. A very interesting ISAC technology is opportunistic ISAC, and I'll give a very interesting example later today on this, where you may have infrastructure of either radar or communications in place, and all you're interested in is that can it double up as if it is a communications infrastructure, can it double up as a radar infrastructure as well with minimum changes in the hardware? That is called opportunistic ISAC. But then there are various other specialized ISAC solutions. If both radar and communications are multi-antenna, then you get joint MRMC. It could be in-band full duplex, which is a technology people are researching these days. There's a lot of talk on intelligent surfaces, and this has led to an ISAC terminology of its own, IRS-aided ISAC. Usually I do a separate talk on just this IRS-aided ISAC because it's very popular these days. And then depending on which part of the spectrum you are in, you can have some specific solutions. So millimeter wave, terahertz. So one example I'm going to provide today is from millimeter wave. If time permits, we'll look into terahertz also. Even the visible light communications community has been looking into joint VLC and visible light positioning systems. And there are some works from quantum community also, joint quantum communications and quantum sensing. In fact, about 15 IEEE societies have at least some working group on this problem of ISAC, or they have published literature related to ISAC in their respective journals. So you can see this problem is very actively researched across various IEEE societies, even non-IEEE societies like ERSI, International Union of Radio Science, as well as various meteorological societies, because we saw an example from meteorology, like AMS or the European Geophysical Union. They also have some working group to examine joint radar communications or spectral crowding problems. So this problem is actually a very serious problem, and that's why in various universities in EE departments, you'll find at least one researcher in all major EC departments who may be working on this problem today. Okay, so with that as the background on where we are in the state of the art, what is the historical context, let's now look into at least one example each of coexistence, co-design, and opportunistic ISAC. And as we move from coexistence to opportunistic ISAC, we move from a very theoretical example to a very practical example. Okay. Let's start with spectral coexistence. As I mentioned earlier, in spectral coexistence, we don't change the transmitter because radar and communications are transmitting independently. We focus on the receive signal processing, how we can mitigate the interference, or if the signal from radar and communications, they are superimposed, how we can separate them. So in this context, we have this problem of dual blind deconvolution. So a few years ago, about 3 years ago, US Army approached us in ARL to look into this problem. I'll come to that, what is the exact problem. But first, let's examine the conventional radar and conventional communications. In conventional radar, we transmit the waveform. So we know what waveform it is. We know the transmit waveform. That waveform then interacts with the target, which for this particular part of the talk, I'll call it the radar channel. And when the signal is reflected and is intercepted by the received signal is the convolution of the transmit signal with the radar channel. Because we know the transmit signal, this problem is a standard deconvolution problem. you can find out details of one of the convolvents because you already know transmit signal. That's how the standard radar signal processing works. You can have a matched filter. It will give you the range of the target. You can do DFT or FFT. You will get the Doppler velocity. And if there is angle involved, you can do your standard Fourier beamforming. You'll also get the angular location. However, there could be some cases where we don't know the transmit waveform. Obviously, we don't know the target profile because that is always an unknown. Those examples could be passive radar, where someone else is transmitting, so we don't know the waveform. Or it could be a hostile entity which is transmitting the waveform. It could be the radar of a hostile country, and they're transmitting the waveform, so we have no knowledge of the waveform. Then at the receiver, you have this convolution. The transmit signal is unknown, and the channel is also unknown. Then how, just by looking at measurements, how can you actually find out both of those convolvents? That is the problem of blind deconvolution, which is a long heritage of rich research in signal processing since 1970s. But last 10 years, people are looking into blind deconvolution even more because we have a lot of advances in signal processing in sparse reconstruction techniques, and they could be exploited to provide stronger results in blind deconvolution. In communications, we have a similar issue. Usually, we estimate the channel a priori, and it's the transmit message that is unknown. So at the receiver, in standard communications, in the convolution that you get at the received signal of the transmit signal and the channel is estimated a priori, and only the transmit signal is unknown against a standard deconvolution problem. But as I mentioned earlier, we are trying to move higher up in the band to millimeter wave and terahertz, where the coherence times of the channels are very short. Even if you estimate them a priori, they become outdated very quickly. Or in dynamic applications, such as vehicular applications, where all these vehicles are moving very quickly, there also, because the channel is dynamic, prior estimates may become outdated very quickly. So you will have a situation where you have a blind deconvolution at the receiver. You don't know the channel and you don't know the transmit signal. So those are blind deconvolution in radar and communication separately. Imagine if it is the case of spectral coexistence, where both of these blind deconvolution signals are overlaid, then you have measured just one received signal, but four unknowns. And in this problem, we wanted to estimate all those four unknowns by just looking at the received signal. So here is the equation at the top, where dual blind deconvolution is described. So we have measurements YT and XR, HR, those are radar transmit signal and radar channel, and then same for communications with the subscript C. Obviously, just by looking at Y, we cannot estimate all four of these signals because there are so many combinations of these four variables that will map to same Y. So it is what we call as an ill-posed problem. The way we can address this is if we know the structure of these signals, which is what people in blind who are working on blind deconvolution usually resort to. If there's some information about the structure, then you can uniquely estimate all four. So that's where we started. For radar channel HR, we assume L targets, and each target is characterized by these three variables. I'm looking at the gray box here. Alpha R, which is the complex reflectivity of each target, which is related to its size, shape, or material used in the target. Tau R, which is delay, which is directly proportional to the distance of the target with respect to the receiver. And then frequency nu R, which is directly proportional to the Doppler velocity or radial velocity of that target. So this is the standard radar channel, but then we assume that radar channel is the superposition of L targets. So that's why we have a summation there. For communications also, we assume Q paths, and then we have a standard delay Doppler channel for communications. For transmit signals, as far as radar is concerned, we pick the most common radar, that is the pulse Doppler radar, which is transmitting a train of pulses periodically. But the pulse, the signal ST, that is unknown to us. We don't know what signal that is because it is dual blind deconvolution. And then for communications, we assume that it is a standard OFDM signal, but we don't know the message GP, that is unknown. So we take all of this structure, put it in the first equation, and that is the dual blind deconvolution because we have two blind deconvolutions. You can also have an n-tuple blind deconvolution if you have multiple emitters. Our work has shown that even that could be solved. I'll come to that in a moment. So we take this structure, put it in the first equation, sample it, and after a few pages of tedious algebra, you can find the details in our paper that appeared last year in IEEE Journal of Selected Areas in Information Theory. You get this last equation here, where there are many unknowns. There are all these channel parameters, that is the range and Doppler velocity of the target. Then similarly for communication paths, those are unknown. And then the transmit signals for radar and communications, those are unknown as well. What we are interested in is to estimate all these by just looking at Y. Even though we have simplified the model, we still do not have an algorithm to solve this. It remains ill-posed. So for the next step, we make the following observations. First is that these channel parameters, they're continuous valued. What does this mean? If there's a fighter aircraft flying at the speed 305 meters per second, normally in radar signal processing, you would estimate Doppler velocity by doing an DFT or FFT of the spectrum. If the bin size of DFT is 10 meters per second, then you can estimate the velocity of the target only as either 300 meters per second or 310 meters per second. But the fact is that it is a continuous valued parameter. The aircraft could be flying with a velocity of 305. How to estimate that continuous value parameter? So we are interested in estimating continuous value parameters. So all these techniques like DFT, FFT, they are ruled out. We cannot use them here. That is first restriction. Second is these channels are sparse, and we'll make use of this fact. By sparse, we mean that there are few targets compared to, and few communication paths compared to the number of pulses we are sampling in the received signal, and then number of discretization we have done in the range domain. So usually this particular constraint is always satisfied because there are just few targets. If we take aircraft surveillance radar, which operates at the airport, then it is scanning a very large area, but the number of aircraft is actually very small compared to the number of points it is sampling in the area. So that's why those channels are sparse. So we'll make use of the sparsity. And the third is what we call as the lifting trick, very popular in blind deconvolution problems. The transmit signals, we constrain them to lie in a known low dimensional subspace. What this means is if you do this, then the problem of recovering all these unknown parameters translates to solving a system of linear equations, underdetermined linear equations, to recover low rank matrices. We want to recover low rank matrices because those matrices encapsulate all the unknown parameters that we are interested in estimating. So that is the implication of those first three observations or assumptions. And after, again, a little bit of algebra, we get this compact discrete signal model. So we have discrete measurements Y, that is the sampled measurements Y. And that is the superposition of these two linear operators, aleph R and aleph C, for radar and communications respectively. And they are functions of these rank 1 matrices, the low rank matrices, ZR and ZC, which encapsulate all the unknown parameters for radar and communications. If we can recover these, we can recover all the unknowns that we have. That is our goal. I want to draw your attention to the structure of ZR and ZC, where we note that they have these complex exponentials within the ZR and ZC, that is e to the power j2 pi and so on. And we know from Euler's formula, complex exponentials, we can write them as sines and cosines. And this fact will come handy when we try to solve this problem. So how do we solve it? Because the channels are sparse, if you look into sparse reconstruction literature, normally when a signal is sparse, that means most of its entries are zero or noise, and very few entries are actual signals, which is the case here because our channels are sparse. Then the classical sparse reconstruction tells us you use L1 norm minimization. You try to minimize the sum of absolute values of non-zero elements. That's a standard technique, which has been popular with sparse reconstruction for about 15 years. Here we have sparsity, but it is not very clear because Channels are sparse, and it is dual blind deconvolution. They are superimposed, and the sparsity is in two domains. It's in the delay domain. It's also in the Doppler velocity domain. So we cannot use standard L1 norm minimization. What we do here is we look into a generalization of this L1 norm, which is known as atomic norm minimization, which was proposed about 10 years ago. It has also been shown in prior works that this is very efficient in estimation of continuous valued parameters, which was one of the requirements of our problem, that you estimate 305 meter per second, not 300 or 310 meter per second for Doppler velocity. So we resort to atomic norm minimization. And if we look into this optimization problem, it is in this box which says minimize the atomic norm. But compared to the standard atomic norm minimization, there are two differences here. We have radar and communications. Sparsity is separate in the channels of radar and communications. So we are going to minimize the sum of atomic norms instead of just one atomic norm. We know from optimization theory, sum of two norms is also a convex function. Norm is a convex function, but sum of two norms is also a convex function. So that is useful. So it is sum of atomic norms, but then each atomic norm, because the sparsity is not in one domain, but in two domains, it's a bivariate atomic norm. And it could be extended to multivariate case also. So this problem, this particular framework is called Soman minimization, sum of multivariate atomic norm minimization. So that's what we'll try to minimize subject to the observations that we have, which we already have. So how to solve this problem? This is the primal problem, this is the main problem, but it is not tractable. We don't have a way to write a code in a computer and then solve this. For standard atomic norm, you can solve it, which is univariate, and there's only one atomic norm. There is a direct semi-definite program for that. For this one, we don't have. So as I mentioned earlier, that this is a very theoretic take on this spectral coexistence problem. This problem, for especially when I do this in universities, people are very interested in knowing what kind of interesting signal processing theories come into play. So in the next 2 or 3 slides, I want to give a very brief overview of what is interesting while solving this problem. So I had mentioned about the sines and cosines, right? Because there are complex exponentials. In mathematical terms, if I have to look at those sines and cosines and these functions, they are called trigonometric polynomials because you can write it as sines and cosines. A simple DFT expression is also a trigonometric polynomial. It's just that we don't use those terms in signal processing or electrical engineering. So we are going to use something special about this trigonometric polynomials, and this work has been around for past 15 years on looking at the spectrum from this kind of mathematical theory. In particular, we are interested in positive trigonometric polynomials. And since, as I mentioned, that this work has been around for some time, there was this very beautiful book that Professor Bogdan Dumitrescu from Tampere University in Finland, he published in 2007. Now a second edition is out, called Positive Trigonometric Polynomials and Their Signal Processing Applications. So what is that polynomial? So I have this polynomial RZ. If it is positive, greater than or equal to 0, if that condition is satisfied, then each one of the coefficients Rk, so Z is the complex exponential. Each one of those Rk's, I can write it as the trace of the product of this matrix theta k, which is an elementary Toeplitz matrix, and a positive semi-definite matrix Q. What is the implication of this result? If I have an inequality imposed on a trigonometric polynomial like this, using this result, I can actually use a linear matrix inequality. We'll see an example of that in the next slide to characterize this PTP completely. So we'll use this result. If we encounter an inequality on this trigonometric polynomial, you can think of it in terms, if you have spectrum and you know that the target lies in certain range, in certain Doppler range, that imposes an inequality on the spectral estimation. If you have that prior knowledge that it only lies, let's say, between 250 meter per second to 350 meter per second, that is the range of the Doppler velocity of the target, that will impose an inequality on its spectral estimation. This is where it comes into play. We are going to see an example very quickly of this. And when we talk about multidimensional cases, multivariable cases, then this positivity is not just greater than or equal to 0, but it's in multiple dimensions. So we call it positive hyperoctane trigonometric polynomials, which is the case of delay and Doppler. Okay, so we have that theory. Now, how do we address that to solve our dual blind deconvolution problem? I showed you the primal problem from optimization theory. If there are only equality constraints, so we had those subject to equality constraints, if you recall, y equal to those measurements, right? Then in that case, if you cannot solve the primal problem, then you solve its dual. Because there are equality constraints in optimization theory, there is this notion of strong duality by the Slater's condition, which tells if you solve the dual, it will give you the exact solution of the primal as well. So we look at its dual. If you look at into the dual problem, which is this first equation, it has those inequalities that you see. There is this term that is smaller than or equal to 1. You take that term on the other side, 1 minus that term that is greater than or equal to 0. You expand it, turns out it's a trigonometric polynomial. And it is positive, greater than or equal to 0, which means that each one of those inequality we can replace using that gram matrix or positive semi-definite matrix that I described as this linear matrix inequality. So each one of the inequalities, polynomial inequalities in the first equation, they are replaced by the matrix inequality in the second equation. Okay, what does this mean? This means this is actually a semi-definite program. We know how to write a computer code for this and solve it. So we started with something that was ill-posed. Then we used this classical signal processing theory to arrive at this problem, which now can be solved. You can actually write a code for this, and you can, given the measurements, you can solve. And the solution would be one polynomial for radar, one polynomial for communications. So from there, how do we get our target parameters? So here is how you get it in terms of proposition theorems for people who are more mathematically inclined, but I'll summarize this, what this means. You get these two polynomials. What we are going to do is we are going to plot their absolute value in a delayed Doppler plane. And these results tell us wherever you see the peak of these polynomials, that is the location of the true delay in Doppler of your target or communication paths. You can think of it like a matched filter. You have an incoming signal, you correlate it with its complex conjugate. Wherever you see the peak, that is the location of the source in case of radar or even TOA estimation problems. So here we are going to look for those peaks. Here is a representation of that recovery, where we are plotting the radar and the communications polynomial, their modulus or the absolute values. And then we try to look where exactly it is unity within some numerical precision. And in the inset plots, you see we have the true parameters, which are the green circles. And the plus sign is where it is unity. They are on top of each other. So you can recover your target parameters and your channel parameters for communications through this process. After you recover it, process for finding the signals, transmit signals straightforward, because then it becomes a deconvolution problem instead of a blind deconvolution. And then you can apply your standard methods to find them out. There are several other extensions of this problem, because sometimes you may also be interested in the angular location. You may want to look into n-tuple blind deconvolution. So I provided some references here. And if you're interested, I'll be happy to talk about it more later on, where we look into various other types of dual blind deconvolution and many other combinations that could be solved by following this theory that we have stipulated in this paper. So that was spectral coexistence, where we saw that these problems of spectral crowding, they actually lead to very interesting signal processing theories and very interesting theoretical problems. Now let's look into spectral co-design, where some hardware is shared. And this is a more practical example from the automotive scenario. We already looked into that bistatic case. Typically, people study bistatic case for automotive applications because it is more general. If you're transmitting in a crowded traffic environment, most likely the signal will be intercepted by another car. Another reason why people study biostatic is, if you look into this graphic on the bottom right, if the transmitter and receiver, they are on the same car, the range of the radar is that red circle. It's equal in all directions. That is the monostatic radar. But if it is a bistatic case, then in one direction you get range extension because the coverage is an ellipse. So it can lead to this incidental advantage of range extension. Moreover, you can see from that graphic, the first one here, where the red car is transmitting and this gray car is receiving the signal, but there is no line of sight between the transmitter and the receiver. So in a bistatic case, you can also do non-line of sight sensing. So those are some other advantages apart from the fact that bistatic or multistatic cases are more general for automotive applications. So in this work that was the runner-up for IEEE Barry Carlton Best Paper Award last year, and this was published in Transactions on Aerospace and Electronic Systems, we looked into the waveform aspect. Whenever we are investigating joint radar communications, usually there are three problems that people look at. First is which waveform to transmit. There are waveforms which are specialized for radar, then there are waveforms which are specialized for communications. How to find a common waveform is always an issue. You can design a customized waveform, but you may not have chipsets that support that customized waveform. So at least in automotive applications, we start with known waveforms. So here we looked into one waveform from which is popular in automotive radar, that is phase modulated continuous wave. And for communications centric waveform, we looked into OFDMA. So that is one aspect of the problem, which waveform you can start with customized, or you can start with known waveforms and then try to customize those waveforms for joint radar communication applications. Second issue is which system you want to optimize more. Is it a radar-centric solution you want, or communication-centric, or both should be optimized, which I referred to that earlier. And the third aspect is having transmitted these waveforms, optimized your design at the receiver, how do you separate the radar part from communications part? So in this particular segment of the talk, we'll look into the waveform and we'll look into the receiver for this co-design question. So here we're looking into PMCW and OFDMA. PMCW has a very good performance in range estimation, and OFDMA has a very good performance in Doppler estimation. Question is, these are their properties in standalone mode. How do they carry forward when we want to look into joint radar communications? For that, in our work, we look into their ambiguity functions. For people who may not be familiar with what it is, you take a transmit waveform, correlate with its delayed and Doppler shifted replica, you get a main lobe, and then you get side lobes. Lower the side lobes, it's better because then you can distinguish two very closely spaced targets very well. So we looked into, we derived their ambiguity function, and it's a very, okay, I don't know why we cannot see this here.
It's faded.
Yeah, okay, it's not faded here. We see. Okay. So when you look into their ambiguity function for the JRC mode, it turns out these children waveform, the JRC versions of these waveforms, they inherit the properties of their parent waveform. PMCW JRC indeed performs well in range estimation, and OFDMA JRC performs well in Doppler estimation. So ambiguity function analysis can tell us this. The question is, okay, once we transmit this, how the receiver looks like. So if we look into the whole analysis for PMCW, the received signal is very complicated, but it has these four unknowns. If you look into these four summations that you see there, that is the received signal, where we are interested in four unknowns to estimate the direction of arrival of the target, Doppler velocity and range, and communication symbols. In PMCW, because it has a good performance in range, you use a matched filter and you can get a very good range estimate. For direction of arrival, you do your standard Fourier beamforming, you can get the angular location also. Then you're left with the Doppler velocity and communication symbols, which are unknown. It turns out after you do the whole analysis, those two unknown parameters cannot be estimated accurately because they are coupled. The residual signal that we see, they are coupled together. You cannot estimate one of them independent of each other. So in our work, we have suggested a way to break this coupling. And that is, we suggest a way of multiplexing. Do not transmit the joint radar communication signal all the time. For some pulses, you transmit radar-only signal. rest of the pulses in that whole observation interval, you transmit the joint radar communications. Then you get some way to decouple this Doppler parameter with communication symbols. Otherwise, it's very difficult to estimate them accurately because they always occur together. In OFDMA, if you do the similar analysis, Doppler performance is very good. You can estimate it using FFT, angle using Fourier beamforming. Then it is the range in this case, which is coupled with communication symbols. So again, employ multiplexing, but this time in frequency domain. Some subcarriers in OFDMA reserved it for radar only transmission, and rest of them are for joint radar communications. Indeed, if we look at the architecture of this joint radar communication system for PMCW and JRC, receiver is very similar. At the receiver, we have the radar processor, communication processor. Communication processor is trying to estimate communication symbols from this jointly received signal. In radar, we first do a coarse parameter estimation where you can get the decoupled parameter very well. And then after we have information from communications about the symbols, communications processor about the symbols, we feed it to the radar processor, remove the communication symbols. It may be perfect or imperfect removal because communication processor is estimating from a joint signal. It is not a standalone signal. Once you remove it, then you estimate your coupled parameter. So the process is same for both of them. Obviously, the transmitters will be different because these are two different waveforms. The only commonality is there is multiplexing in both cases. In PMCW, it's in time domain, or FDMA, it's in the frequency domain. I want to end this segment by giving an example about how multiplexing works in this case, how it could be beneficial. So here we compare the two waveforms, their performance. We look into the coupled parameters estimation error. OFDMA, the coupled parameter was range. PMCW, it was Doppler. So I'm looking at these B and D plots. So in the B plot, you can see the red curve is the theoretical curve. That means the communication symbol removal is perfect. And then if it is perfect, when you remove it from your residual signal, you can very accurately estimate your coupled parameter. So that is our red curve. Then the blue curve is the case when the communication symbol removal is imperfect and you do not do any multiplexing. All the time you're transmitting joint radar communications. Then when the SNR is high, blue merges with red. You can estimate the coupled parameter actually fairly well if you have very high SNR. But usually in radar systems, it's a low SNR system. If that is the case, then we see that the two curves, they diverge at low SNR. However, if we decide to do multiplexing, half for radar communications and half for radar only, that gives us that gray curve, which at low SNR betters the performance of the blue curve. So that shows that multiplexing could be practically useful in this case. So at this stage, I want to move on to this opportunistic ISAC example, so we started from a very theoretical one, then we did a mix of theory and practice. Now let's look into this very interesting example of opportunistic ISAC. And this is an example from weather sensing. So recall in opportunistic ISAC, you already have infrastructure of either radar or communications, and you want it to develop as the functionality of the other system, right? So here is the problem that we had. So this European telecommunications company, whose name I cannot reveal because of proprietary reason, approached us to address this problem. Usually when you want to look at weather, we have weather radars. So in the contiguous United States, we have about 140 S-band radars operated by National Weather Service, which cover more or less the whole continental US. But these systems are very expensive. And in Europe and Canada, usually it's a C-band, but they are also very expensive, very bulky and big systems. Further, as you move away from the radar, the lowest elevation beam after about 80 kilometers starts touching the cloud tops. You don't see anything that is happening in lower troposphere, which is where the precipitation is. So there are still practically gaps in the coverage of these radars. Then we have developing economies where these expensive systems have not been installed and we don't get any weather sensing performance there. So we were approached by this telecommunications company, and they said they have a lot of ground-based communication satellite terminals where the signal is coming from the satellite and reaching the ground. So it is going through the atmosphere and it is getting attenuated because of rain. Can you use that data to actually complement with the radar and estimate rainfall rate? And this is very lucrative because there are about 300,000 such terminals just in Europe and about 2 million worldwide, even in developing economies where there is no weather radar. So can we use this information to estimate rainfall? That was the challenge that we had. Now in weather radar, because it is specific to that application, you transmit the signal, you get the distorted signal back. There's wealth of information that you get back. You get Doppler velocity of the storms and so on, and you can very accurately estimate rainfall. But here, all we get is the transmit power at the satellite and then the receive power. Receive power is much lower, so you can estimate the attenuation between them. Can we use that to estimate rainfall? So ITU specifies that at millimeter wave, these are millimeter wave communication satellites, the relationship between rainfall and specific attenuation is the first derivative of attenuation with respect to range. It is linear. And they provide some formula so that you can roughly estimate rainfall. But in practice, that formula doesn't work, especially in the presence of wind shear when the storms are very convective, moving very fast. Then this linear relationship is perturbed. You cannot use that to accurately estimate rainfall. And we don't have radars either. So again, we have this problem, how to use attenuation to estimate rainfall. So normally these days, in every presentation, there comes a point where you encounter deep learning. This is our contribution to a deep learning application. Because we don't have enough information, we use a deep learning network, train it with the nearest weather radar data in the training stage. And then in the prediction stage, we input this attenuation data from the satellite and then see what it gives us. So we started with this very first example in Southwest Germany, where we had about these 30 user terminals that you see in that box, the black dots. That is the location. So this is at the border of Luxembourg, Belgium, and Germany. And we had data from those terminals. We trained it with the nearest German weather service radar, or the DWD radar, of a neural network. And then in the prediction stage, we provided data from these terminals to see what it gives us. So first, we picked just one terminal. And that is this, the bottom plot that you see, the red curve is the rainfall estimated by the neural network using the satellite link data. And then the DWD radar is the blue curve. It very closely follows them. But meteorologists, they don't use this. Meteorologists look at accumulations, cumulative rainfall over a time. And when you look at cumulative rainfall over the time, it keeps on diverging from the radar, what radar is predicting. The satellite link is overestimating it, and that gap keeps on widening. This is so we'd like to improve this. This is for just one terminal. When I do this for all these 30 terminals, and I can create a map of rainfall. Let's look at how that map looks like in our first attempt. On the right side is what German weather service radar is seeing. There's a storm moving towards the northeast, and then using our method, the satellite link, we get these plots on the right side. So radar is always very accurate because it has so much information. Here, all we had was the attenuation data. So when we started with this problem, then these were the first results we got, where okay, the direction is probably more or less right, relative intensity, but it's nowhere looks like close to the radar data. Meteorologists, they cannot use something like this. So we wanted to improve this. And what we did is, here we had 20 terminals. The next part is, if you get more data, can you improve this? So we got access to data from France, where there were about 12,000 terminals. So from 30, we go to 12,000 terminals, and then we train our neural network for those 12,000 terminal data. Here is what we get. On the left side, in the first panel, you see what the Meteo France radar is seeing, a storm in 2021. And from our satellite link is that figure on the right side. very close to each other. We don't see these blobs or anything like that. And then the bottom two panels are every 3-hour comparison between radar and the satellite. So it's not very surprising because neural networks require a lot of training. And if you can have a lot of data to train them, you can get better results. Another representation of this is this movie where we had this storm in 2020. And you can see on the, so I'm seeing it very correctly here. It looks very nice, but I don't think it appears like that.
Yeah.
Do you see that?
No, it's just fading out a little bit, but yeah.
Okay. So, well, it's a circulation that is captured very well. So on the right side, you see the satellite link and all those black dots that you see, those are those 12,000 terminals. And on this side is the Meteor France. So even when there is an outage in some of those terminals, even then you get some rainfall estimation for those locations. So this is a very good example of how you can use communications to actually complement observations of radar. We have done this for Germany as well. Now we are doing it for Brazil. One of the challenges is to do this for Switzerland, which is this mountainous terrain, and there is a lot of blockage there. That is one of the areas of improvement in this problem. But other than that, at least for terrains like these, you get pretty accurate results, which meteorologists can actually use. As I mentioned earlier, it's very difficult to summarize all kinds of activities going on in this area. We have done a lot of work on various other types of ISAC. You can refer to the references that I provided here. We are also looking into the use of 5G waveforms to use it for monitoring the heart rate or respiratory rate of drivers and other passengers. So that is ISAC-based vital sign monitoring. A few other architectures are listed here. For drone-borne ISAC or using IEEE 802.1180 protocol, which is also very popular for joint radar communications these days. One thing I want to highlight here is when we open up radar and communication systems for sharing of their hardware and sharing of other details, then the security of radar systems and privacy of communication users could be compromised. So there is a lot of recent focus on secure and privacy preserving ISAC. We have also done some work on it. You can find more details in our references that I've mentioned here. All right, so at the end of every YouTube video, you have like, share, subscribe. Now, there's not a YouTube video, but if you're interested in my research, please feel free to follow me on LinkedIn, where I regularly post updates about my latest papers and upcoming talks. We also have a book where you'll find a lot more details on joint radar communications. It is published by Wiley IEEE Press. You would have guessed by now, I'm quite interested in weather radar. So we have published a 3-volume compendium recently. It was published 2 months ago on all the advances in weather radar in past 10 years. It's a pretty good reference book. I mentioned about all the trigonometric polynomials in high dimension. So I'm actually editing a book on multidimensional signal processing, where if you're interested in more theoretical problems in the domain, it will be published in 2026. So with that, I would like to thank you, and I'm happy to take up any questions you guys might have. Thanks.
I have a question. In the diagram where you have multiple vehicles and the signals being reflected off of the vehicle and received by a separate vehicle, does the speed difference impart Doppler effect on the signal? And is radar Doppler and position information available off a reflective surface, or does it have to be a direct transmit to receive?
The Doppler of the target, you mean?
Yes, but
Yes.
Does the reflective surface velocity impart Doppler onto the signal, and does that mess up the?
Of course, yes. So when you get this received signal, it is modulated by that Doppler velocity.
Right.
And after you remove the carrier frequency at the baseband, then normally you estimate that Doppler velocity, the modulation using DFT. So yes, it indeed shows up in this problem. But then it's not like a simple bistatic radar, because you have communication symbols. If you're using OFDMA, then you can estimate Doppler right away from the received signal. Just apply DFT, you'll get it. But if you're using PMCW, then you cannot estimate that Doppler velocity, that modulation, because it is coupled with unknown communication symbols. And that's why I was talking about this multiplexing, if you want to get that Doppler.
Right.
Yeah.
But even in the case where it's not a shared communications channel conveying communications and radar information, if it's just purely radar, does having a reflective surface still provide accurate radar?
Of course, because the target is moving. So when there is movement, then the signal is going to get modulated by the rate of that movement.
Right.
Yeah.
But on the reflective surface car T1, I think it was on top, if it has a different relative speed than the receiver and the transmitter.
Okay. Yes, of course. So receiver and transmitter, I mean, because, well, in these problems, we assume that we know their Doppler because the receiver and transmitter, if they know their transmit waveform, they have to know other parameters of the platform. So that Doppler is known for the receiver and transmitter. The only unknown is that reflective surface,
Right.
which then we estimate.
Oh,
So yes.
okay. Thank you.
Yes.
Do you also use MIMO to help reduce interference between communication and radar channels?
To help reduce
Interference, to help remove the interference between.
So, well, so MIMO is, it operates very differently for communications and radar, right? So I mentioned this joint MIMO radar MIMO communications, one of the topologies, MRMC, that is about looking into MIMO. But how MIMO could be used to reduce interference? Essentially, in angular domain, you get another degree of freedom because you're using multiple antennas. So you can reserve some antennas for radar, some antennas for communications. And that even if the spectrum is common, because the antennas are different, in spatial domain, you can use that degree of freedom to separate radar from communications. But MIMO for radar and MIMO for communications, they're two completely different things. MIMO communications we use to intelligently spread information across different antennas, then use spatial diversity, spatial multiplexing to actually increase the data rate, lower the error rate. But in MIMO radar, we don't have any communications. MIMO radar, why it is popular, at least in automotive cases, you can use fewer number of antennas and get the same resolution as a phased array. Since in automotive scenarios, we have size constraint, cost constraint, it is very attractive to use MIMO because fewer antennas, but the same angular resolution. But then there is a cost to this. You will have to transmit mutually orthogonal waveforms for radar. Communications, you don't do that. Yes, you can use it to separate the two, but it comes with some cost. That is design of orthogonal waveforms. And then in the digital domain at the receiver, at least in radar, you have many matched filters that you will have to use. Not in analog domain, but digital domain cost may increase because of that. But it is only popular for automotive applications, MIMO radar. For military, we do not have any MIMO functionality because when you use mutually orthogonal waveforms, you cannot form a coherent beam. Your overall SNR comes down. So military is interested in surveillance and tracking. You cannot do those tasks when you don't have a coherent beam. So phased array, very good for tracking. MIMO, very good for imaging because it illuminates the entire area at once. There's no coherent beam. Since in automotive radar, we are not doing any tracking, it's mostly imaging, this kind of technology works in automotive applications. So for automotive, you can use MIMO as another degree of freedom to separate radar from communications, even if they're using the same spectrum. So just a few more details. Yeah.
Are there any, I think I saw on one of the rain sensing application, there was some deep learning references. Are you using any kind of LLMs that you build in-house for optimization?
We haven't used LLMs for these applications, but yes, I mean, the learning applications are mostly for millimeter wave and terahertz, but the application of those architectures is in hybrid beamforming. When you go to higher frequencies, attenuation is very high at millimeter wave and terahertz. I mean, we know attenuation increases with frequency, but the increase is not linear. Still, it's very high at millimeter wave and then much higher in terahertz band. The way to compensate for that is that you use very large arrays at those frequencies. And since lambda over 2 will be very small, higher frequency, smaller wavelength, you can have a compact array placement with lot of antennas. But then if I have those many number of antennas, I need an RF chain for each one of those antennas. And the number of antennas has, let's say, increased 10 times. My RF chains and all the components in RF chains, that also increases 10 times multiplied by all the components I may have. If I have, like, let's say 8 components every RF chain, so I have 80 more components that I have to deal with. So the size of the whole system is bigger. It could be expensive, power consumption may rise, and already in 5G, we want low cost, energy efficient, those kind of system. So implication of all of this is when you have a large array, which you can't help with, you will have that because you want to fight this attenuation loss at those frequencies through beamforming gain. But then you can't have a dedicated RF chain for each one of the antennas. The only solution is you use fewer RF chains than the number of antennas. But if you do that, then you cannot do fully digital beamforming. You will have to do some beamforming in analog domain. You will have to use some phase shifters now. So this is what we call as hybrid beamforming. At millimeter wave and terahertz, because of the large size of the array, fully digital beamforming is infeasible. So we split the beamforming in analog and digital domain. If you do that, then the hybrid beamforming beamformers that you need to find, that is a very computationally intense task. You have to solve all these non-convex optimization problems. There is no closed form expression, so on. So what we look into our work is we use deep learning to actually find out hybrid beamformers on the fly. So you train during the training stage, you still have to solve those problems, but that is all offline because you're training the network. Once the network is trained, post-training complexity to find out hybrid beamformer for these applications is very low. So most of the works that people look into using deep learning for joint radar communications is solving those kind of higher dimensional problems, which may take a lot of time. So hybrid beamforming is one of them. Sometimes it is combined with channel estimation also. If you have now 300 antennas at terahertz, obviously channel estimation, you have to do the singular value decomposition of a matrix, could be very challenging. Instead, you could use deep learning. So that is the application.
We have now come to the top of the hour. Thank you, Dr. Mishra, for your very informational and insightful session on the new frontiers in integrated sensing and communication and your exploration on the use cases. We truly appreciate your presentation. I will be remiss for not acknowledging Plana System and specifically Praveen Shuburu for giving us the privilege of using this great facility. And thank you all and have a great evening.